In this lesson, we will explore Young's double slit experiment. When a single light source passes through two narrow slits, S1 and S2, they act as coherent sources, emitting light waves that overlap and interfere with each other. To derive the fringe width, we define our geometry. Let the distance between the two slits be smalls d, and the distance from the slits to the viewing screen be capitals D. This setup allows us to observe the interference pattern. Consider a point P on the screen at a vertical distance y from the center. The light from S2 travels a longer distance than light from S1. This extra distance is the path difference, which determines the type of interference at point P. Using geometry, the path difference x is equal to d times the sine of the angle theta. For very small angles, we can approximate this as d times y divided by d. This relationship is crucial for our derivation. Constructive interference occurs when the path difference is an integer multiple of the wavelength, lambda. This results in bright fringes on the screen at positions y equals n a times as lambda d over a d. Destructive interference happens when waves arrive out of phase, specifically at half-wavelength intervals. This creates dark fringes where the light waves cancel each other out, resulting in zero intensity. The fringe width, denoted by the Greek letter beta, is the distance between two consecutive bright fringes or two consecutive dark fringes. It represents the thickness of one complete fringe cycle. By subtracting the position of the nth fringe from the n+1 fringe, the terms involving n cancel out. This leaves us with a simplified expression for the spacing on the screen. The final formula for fringe width is beta equals lambda times capitals D divided by smalls d. This shows that the width is directly proportional to the wavelength and the distance to the screen. On the screen, we see an intensity distribution where all bright fringes have the same intensity. The central maximum is located at the center, where the path difference is exactly zero. To summarize, increasing the wavelength or the screen distance will increase the fringe width, making the pattern more spread out. Conversely, increasing the distance between the two slits will make the fringes narrower and closer together. Young's experiment provides definitive proof of the wave nature of light. By measuring the fringe width, we can accurately determine the wavelength of light used in the experiment. Generated by Vision Solve AI.